Alright folks, so I thought I would do a little chapter 1, chapter 2 intro video just to kind of give you a little direction here. So I wanted to also just reiterate where you can find the textbook. So if you go to the course home and scroll down under course resources, there's the Anatomy and Physiology textbook. Or you can simply go into Google or wherever and just type in Openstax Anatomy and Physiology, or even just Openstax, and then follow the subjects to science, and it's usually one of the first ones that pop up, right? So they're Anatomy and Physiology and view online. That's one of the easiest ways to get to it, and so you can always go there or just search it. Super easy. So I thought I would just do kind of a quick review or just a quick overview of chapter 1, chapter 2. There's some PowerPoints there for you. I won't always have PowerPoints because those are pretty bare bones, and I just have it for you to kind of look at for a bit of an overview. These Windy Rigs videos are pretty comprehensive, and so I don't really feel like I need to redo those necessarily, but that's why I'm doing this, so you'll have a chance to kind of see me a little bit, and we can talk about some things that I think are important. So I'll try to keep these videos relatively short. Chapter 1 is just that. It's an introduction. So you're going to talk about maybe the difference between, so what is anatomy, what is physiology. Some colleges do courses that are just anatomy and just physiology. So you would have a semester long of just the anatomy of the human body and then a semester long of just the physiology. I think it's a little better to put the two together. I think anatomy by itself gets a little boring, and physiology by itself gets a little complex. And so I think when you can put the two together, it makes it a little more digestible. That's what I think, right? Typically, we'll talk about gross anatomy, so that means things that you can see kind of with your naked eye. Not on the surface necessarily, right? So your intestines, you could talk about those, the gross anatomy of those, just because you could see them. But also when we talk about tissues and things, we can talk about the microscopic anatomy. So what makes up the tissues and how are they different microscopically. One of the big things, so in this chapter they talk about structure, and if you've taken any science class, you've probably talked about this a little bit, right? So from the atom all the way up to the organism. In this chapter we talk a little bit about what does it mean? What do you have to have? What does it mean to be living, right? So you have to have things like metabolism, you have to have responsiveness, which a lot of times responsiveness we talk about as movement, not necessarily. Responsiveness could be any kind of change based on a stimulus. So if your, for instance, blood sugar changes, your body's going to adapt to that, and that's a responsiveness too. It's not just a movement. We certainly move. What are the requirements to life? So things like oxygen, we need that. Not all living things do, right? Plants, for instance, that's a waste product for them. Right, but we need oxygen, we need certain nutrients, whether that be macro or micro nutrients, and so your book talks a little bit about those. So micronutrients, that doesn't mean they're not important. In fact, they're probably more important. Those can oftentimes be coenzymes, which we would talk about as vitamins. So you don't need much vitamin C. Certainly this time of year, one of the things that you see folks do is they'll megadose on something like vitamin C. Vitamin C is super water soluble. Your body's only going to use the amount that it needs. The rest of it water soluble and goes out in your urine. And sometimes if you take a multivitamin, just to kind of jump right into some gross anatomy, if you will, although if you're going into nursing or things like that, you'll have to get over that part. But if you take a multivitamin, one of the things you might notice is that it can and will change the color of your urine. Why? Because most of those vitamins are water soluble, and if your body can't use them, ends up in your kidneys, ends up in your urine, and you just get rid of it. And so you oftentimes don't need to take those mega doses. It doesn't really do anything for your immune system like people would think. But whatever, I can say that stuff. If taking it somehow eases your mind, then by all means, it's there's not a great deal of research out there that would suggest that they're going to hurt you necessarily. They're just expensive, though, and that's my problem. We operate in a relatively narrow temperature range. Right? Our body needs to say 98.6 plus or minus. And if we get outside of that, I know I got my booster for COVID about 2 or 3 weeks ago, I think. I had a mild fever the next day for just a few hours of 100. So from 98.6 to 100, that's not much, but I did not feel great, and that was mostly due to the fever. Right? Yeah, so we operate in that pretty narrow range. Pressure is also one that we don't think about too much. The pressure can't change too much, or we're not going to like it. For instance, when you get to the top of Mount Everest, the pressure is relatively low up there, and what that means, really all pressure is, so when you're here at whatever elevation you are, the reason the pressure is there is because all the molecules of stuff that are above you through the atmosphere. So as you go higher and higher in elevation, there's less that's above you, and so the pressure is less. Some people will say there's less oxygen up on the top of Everest. That's true. Percentage-wise, it's still about the same. It's just there's less individual molecules, so there's not as much oxygen up there for you to get into your lungs. And a lot of that's just is pressure-driven, so it just causes you some real problems that we term altitude sickness. So you need to adapt to those kind of things. Although you never really adapt to Everest elevation. You can adapt to higher elevations, but up there, where they term the death zone, that's a bad day. The opposite, though, is also true. So if you go diving and one of the problems with diving is you're underwater. So think about all the water that's on top of you now. That really puts a lot of pressure on you. It causes a lot of gases that would normally not dissolve in your blood to dissolve in your blood, like nitrogen. So if you come up all of a sudden, all those gases are going to try to get out of your bloodstream, and that can cause you problems, right? So we talk about decompression sickness there. One of the big things in this first chapter, and if I was probably going to ask you a short answer question on an exam later, it would probably have something to do with these feedback mechanisms, though. These things are hugely important, especially later in chapters when we start talking about, how do hormones function or whatever. It's all through these feedback mechanisms. And so we can essentially have two types. We can have negative feedback mechanisms, and we can have positive feedback mechanisms. The way to think of a negative feedback mechanism is it wants to change the direction of whatever that stimulus is. The easiest one, I think, for most students to kind of conceptualize is the one they use here, body temperature. So as your body temperature either goes up or goes down, your body wants to change that direction. So as you get too hot, your body wants to cool itself down, right? So that's a negative feedback. Your body gets too hot, you start to sweat, the sweat evaporates, and it cools your body down, right? As you get too cold, right, then what happens? Well, you want to start to shiver. And as you shiver, your muscles release heat, and that kind of helps to bring your body temperature back up. Right? And so those are negative feedback mechanisms. So you have a stimulus, and this is true for any feedback. You have a stimulus, a sensor, a control, and an effector. Right? So if you're looking at body temperature, right? So if it exceeds 37 C, which is about 98.6 degrees, the nerve cells on your skin and your brain kind of interpret that. Those regulation centers in your brain tell your body to release some sweat, and then that affects your body temperature by bringing it down, right? Negative feedbacks. Negative feedbacks are the most common feedbacks in us. They're pretty safe. These don't tend to really necessarily get out of control too much. But a lot of things are regulated by this. Blood sugar, for instance, if blood sugar gets too high, your body's going to bring it down. If blood sugar gets too low, your body's going to bring it back up. And we'll talk about the mechanisms later, probably. So this is 168. We'll probably talk about that more in 169. Right? Positive feedback mechanisms, though, are a little different. So if I went back up here and I changed, if our bodies were to work on positive feedback loops for temperature, as your body temperature went up, the positive feedback loop would make the body temperature continue to go up. So positive feedbacks, instead of changing the direction of the system, positive feedback loops continue it, right? And so the classic example that books use is birth, right? So here, your brain and the pituitary gland releases this oxytocin that's carried into the bloodstream, causes the uterine contractions, which pushes the head of the child against the cervix, which then causes another stimulus to go to the brain, which causes it to release more oxytocin. So oxytocin release, contractions, causes pressure against the cervix, causes more oxytocin release, more contractions, so on and so forth. And so that just continues, right? And any of y'all that have had children, you know what those contractions are and how they just keep coming and coming and coming. The thing about positive feedback loops, though, is there's usually a definitive end to whatever that feedback loop is operating on. So here, the definitive end is childbirth. The child is born, and that's that, right? Although, if the child's not born soon enough, this can cause a problem, right? And so positive feedback loops can get out of control a little bit if whatever the thing they are controlling doesn't happen in a given amount of time, right? But that's kind of the classic example of a positive feedback loop. And so maybe I would want you to tell me what's the difference between positive and negative feedback loops, and give me some examples. See if you can find some other examples other than your book gives you a different one, but see if you can find another example other than childbirth, and see if you can make that make some sense there. But that's kind of the big thing in Chapter 1, feedback mechanisms. That's the big takeaway. Chapter 2 talks about chemistry. This one talks about atoms and what are you mostly made up of, and what are atoms and what are chemical bonds, ionic bonds versus covalent bonds. And I've given you, I'm pretty sure I gave you some videos on those, right? So here's some chemistry videos. What does it mean to be an ion, right? Ion or ionic bonds have charges like positive and negative charges. Cations are positive charges, anions are negative charges. But probably the big thing that I'll focus on here with you in Chapter 2, the big takeaway would probably be these macromolecules. So macromolecules, macro for large molecules, they tend to be the things that build us, right? The things that we need in our diet. If you've ever been on a diet, you've probably heard people say, count your macros. Well, what do they mean? This is what they mean. Some diets even tell you to avoid certain macros altogether. I would tell you those diets are not sustainable, and you should not try. It's not that they're dangerous necessarily. They're not sustainable though. So a lot of times, one of the big things that diets will tell you to avoid are carbohydrates, right? So they'll just say, don't consume any carbs, no starch, no sugar. The problem with that is most people like them. And so if you are forced into avoiding something that you like, sometimes that can create issues where you don't have the best relationships with food. And so you start to think about food in the wrong ways. What I tell people that are trying to diet at all is the best thing to do really is just to count calories. Know what healthy weight loss is if you're trying to lose weight, for example. Healthy weight loss, really, most people overestimate what that should be. It should be about 1/2 to 1 pound a week. And I know that doesn't sound like a lot, but if you were to lose 1 pound a week for a year, that's 52 pounds. That's pretty dang good. And so if you're on diets that tell you to avoid macros altogether, unless you have some medical condition, right? And there are some medical conditions that would require that or would benefit from that. Just be careful of those and watch those and make sure you're not creating, kind of bad habits with food and bad relationships with food. But if we talk about carbohydrates, so carbo for carbon, hydrates for hydrated or water, and if you see the formula for carbohydrate, carbon, C, and water, H2O. That's their formula. They come in a bunch of different types. So for instance, monosaccharides, mono for one, saccharide for sugar. That's things like glucose, right? Glucose is hugely important to us. So back to the diet thing. Some people will tell you to avoid sugar. Some people go even as far as telling you that sugar is toxic. Well, no. Your mitochondria take sugar and make ATP from it. And we'll talk about that later in the semester. If sugar in and of itself were toxic, why on earth would you have an organelle that's responsibility is to give you tons of energy from that thing, which is sugar? So it's not toxic. The problem is too much, right? So again, you can count calories and you're fine. But there's a bunch of different types of monosaccharides. So glucose, fructose, which comes from fruits, galactose, ribose, deoxyribose, and we'll talk about those when we talk about DNA and RNA, respectively. Then we can take two of those monosaccharides and put them together to give us disaccharides. So things like sucrose. This is your table sugar, right? So notice table sugar really is. So it says monosaccharide glucose and fructose. So take those two, right? Glucose and fruit sugar, put them together, and you've got sucrose. Again, you probably don't want to sit down and eat a bowl of sucrose, but in and of itself, there's nothing toxic about that, right? Lactose, which is milk sugar, right? So galactose and glucose together. And then maltose, typically you find maltose in grains. So if you think about malts, one of the ways that you get sugar to ferment beer is through malting, or taking the grain and the maltase and producing maltose, which is the sugar. And so that's two glucose molecules stuck together, right? So those are disaccharides. When we get more than two, we just start calling them polysaccharides. These could be things like starches. Think about potatoes, right? Full of starches. Glycogen. Typically, mammals will store carbohydrates in the form of glycogen. You'll store a lot of this in your liver. So you go to sleep tonight, and as your blood sugar level starts to drop off a little bit, your liver stores some glycogen, and you'll use a hormone to break some of that glycogen down, release it in the form of sugar into your bloodstream, and then your blood sugar stays relatively neutral. And then things like cellulose. So this is what trees are made of. The hard stuff that is a tree. You don't digest that very well or at all. In fact, things that do digest it well, like termites, so a termite needs a protist that has a bacterium in it, and that's how they break that stuff down. But you can find cellulose in a lot of places. We tend to call it fiber. But you do need that. You do need fiber in your diet. You just don't digest it well, and that's kind of the point, right? The functions of carbohydrates I've already alluded to. It gives us ATP, and a lot of it, right? It's energy. That's the reason you like these things, though, right? Like, it's not a coincidence that you like sugar and you like starch. There's a lot of energy in there, and it's quick energy, and that's the reason we like them. Right? Same thing with lipids. Lipids are fats, oils, and waxes. Sometimes we call them triglycerides because they look like this, right? So glycerols, 3, and 3 fatty acids, so triglycerides, and that's what they tend to look like. Right? Some differences between lipids is they can be saturated or unsaturated. All that means is a saturated lipid has as many hydrogens around it as it can possibly have, and unsaturated doesn't. So notice that double bond there causes it to kink a little bit. Well, why does that matter? Saturated fats tend to be things that are solid at room temperature. So think about butter, right? If you leave butter out of the refrigerator, it doesn't melt, right? It stays solid. Unsaturated fats tend to be liquid at room temperature. So think about olive oil. Right? You leave olive oil out at room temperature and it stays liquid. You put it in the refrigerator or even the freezer, obviously it kind of coagulates a little bit. Right? But the other lectures go into a little more detail. One of the most important lipids, though, are the phospholipids. So they look different in that they only have 2 parts to them. Phospholipids make up your cell membranes. Without them, you would not have a cell membrane. And so that's kind of what they look like. Some other lipids are steroids. Steroids aren't just, most of the time when people say steroids, they think about maybe anabolic steroids for building muscle. Steroids have a huge role. So they can be everything from cholesterols. Cholesterols are not always bad. They've got a bad name for them in the past probably 20 years. They just cholesterols help stabilize cell membranes. If you have too many cholesterol or too much cholesterol, it makes cell membranes too rigid. But if you don't have enough, they'll fall apart. And so you have to have a decent amount or the right amount in cell membranes, right? And so those are steroids. Steroids can also help with inflammatory responses, right? So if you've ever had to take prednisone, right, that's a steroid that helps with that. I don't talk too much about the prostaglandins other than for you just to know that they are a lipid. Right? And then if we talk about proteins, that's another. So carbohydrates is one macromolecule, proteins is another macromolecule, lipids is another macromolecule, right? So proteins do have a role in storing maybe some energy, a little bit more energy than carbohydrates. And I guess it should say per gram, lipids store the most energy. Right? Again, it's not a coincidence that we store fat. Right? Why would we store excess energy as fat? Well, because you can store the most energy in the bonds of lipids or fats. It's also why it takes so long to get rid of it. You have to do so much work in a calorie deficit in order to get rid of that fat because there's so much energy in it. Right? But proteins are built of amino acids. They make a lot of the structure of us up. They're put together by these bonds called peptide bonds. Oftentimes they're just indicated by spheres. So that's an amino acid 2, amino acid 3, 4, 5, up to 20. So we'll have 20 amino acids. You either have to consume the amino acid because we don't make them all, or you can. There are a few that we do make. The way they go together, right? So they either have this primary structure, which is just a chain. They have this secondary structure, which is either this alpha, it's called an alpha helix, right? So notice there, or this pleated sheet. Or they have this tertiary structure. So take these helices and these sheets and stick them together, right? That would create this tertiary structure, which looks kind of like a ball. Or if you see one in kind of 3D animation, it just looks like a mess. And then if we take several of these tertiary proteins and put them together, we can form a quaternary structure, and this just happens to be what hemoglobin would look like in this form, right? And so those are proteins made up of amino acids. Right? Proteins can also function as enzymes. Enzymes are just things that speed up or, well, I shouldn't say slow down. Enzymes are things that speed up reactions. Right? What do I mean by that? Well, sucrose, for instance, which I already talked about, I could take sucrose and put it on a table, and over time, because it's a pretty high energy molecule, it would break apart, would release some CO2, maybe leave some water behind, but it would take years. You don't have years to get energy, right? When you drink your coffee in the morning that you put sugar in, you want to get energy from that pretty quickly. And so enzymes help you do that. Right? So with an enzyme, here they're showing you maybe putting something together, right? So you have your substrates with the enzyme, comes together and produces your product. Well, the opposite can be true too. So if this were sugar in the enzyme, right? So sugar binds with the enzyme and then is split apart and maybe gives you CO2, water, and releases some energy for you to use. But the important thing about enzymes is that they speed up reactions, and they are typically proteins, not always. Sometimes they can be RNA, which are called ribozymes. Right? What else? The last macromolecule are nucleotides. Nucleotides mostly carry information, so RNA and DNA. Maybe you've heard them called nucleic acids for RNA and DNA. Right? So deoxyribonucleic acid and ribonucleic acid. I'm not going to go into a huge amount of detail about DNA or RNA. Probably not hugely important here, and we can talk about it later in the semester, or maybe in 169 when we're talking about genetics a little bit. ATP, or adenosine triphosphate, does happen to be a nucleotide. Right? It's just an adenine molecule with 3 phosphates stuck to it. Right? So there's your adenine with 3 phosphates. And the energy is in the bond there. So if I break that phosphate off, I release energy, and then your cells can use that energy to do work. Right? And so that's what this is showing you. So ATP plus water, right? We're essentially a sack of water, would give us ADP, right? So if adenosine triphosphate loses a phosphate, it becomes adenosine diphosphate plus that 1 phosphate molecule that is used later, and some energy, right? So that's 2.5 is definitely the big take home for this chapter. I'm not saying that's the only thing to pay attention to, but macromolecules. So carbohydrates, lipids, proteins, nucleic acids. What are they? What are they made up of? That's important. The inorganic things are things like salts. You definitely need salt. You definitely need water. Water is inorganic. I guess I could spend a minute talking about those two things. Because in the common vernacular now, the word organic has gotten stolen a little bit from science and chemistry. Organic simply means carbon-hydrogen bonds. In science, it has nothing to do with, is it natural or not, or is it have no pesticides or not, right? It has nothing to do with that. In science, organic means contains a carbon-hydrogen bond. So things that are organic contain that. Things that are inorganic don't contain carbon-hydrogen bonds. So water has no carbon in it, right? This HCl, that's an acid, right? That C is not carbon, that's for chlorine, right? So hydrochloric acid. Carbon dioxide, it's got carbon in it, doesn't have hydrogen in it, so that's considered inorganic. Salt, right? Salt, table salt, is sodium chloride. So no carbon in there, no hydrogen in there, so that is an inorganic compound. So organic compounds contain carbon-hydrogen bonds, inorganic things do not. Right? What else? Water, hugely important to us. You should read all of these bullet points about what water does and why it's important. One of the big things for us is it helps us maintain our temperature. You might have noticed before that water doesn't change temperature very quickly. So if you boil water on the stove and then turn the stove off and come back in an hour, that water is still pretty hot. Right? Why? Because it has the ability to hang on to that temperature. It doesn't cool off very quickly. I mean, think about a piece of aluminum. If you put a piece of aluminum on the stove and turn it to high and leave it there just as long as you did the water, cut it off, come back in 30 minutes and you can certainly pick that piece of aluminum up. It loses heat pretty quickly. Water doesn't. Right? It's going to hang on to it for a long time, and that's good for us. Right. What else? Salts, acids and bases. So the big thing about acids is they tend to release these hydrogen ions. So if I take hydrochloric HCl acid and I put it in water, it releases a bunch of hydrogen ions. Whereas if I take something that's a base, right, like sodium hydroxide, right, they should, it's NaOH. I don't see that here. Typically they'll put NaOH. Anyway, if I put something that's basic in water, it'll release a bunch of hydroxyl or OH ions. Most people assume that acids are more harmful than bases, and that's just not true. Strong bases are just as problematic for us. In fact, really strong bases are better able to break down tissues than are acids. So if you've ever seen Breaking Bad, they used hydrofluoric acid there to break down tissue. It'll do it. It's just not the best. Right? I mean, there's plenty of bases that would have done that better, but that's Hollywood for you, right? And then pH is just the measure of how acidic something is, right? So the pH scale goes from 0 to 14. Things that are 0 are really acidic. Things that are 14 are really basic, and things that are 7, neutral. Right? And one thing to remember about this pH scale is it is logarithmic. So as I go from pH 7 to pH 8, pH 8 is 10 times more basic than pH 7, not just one time. Right? So pH 9 is 10 times more acidic than pH or basic than pH 8, and pH 9 is 100 times more basic than pH 7, right? Because it is a logarithmic scale. What buffers do is kind of keep all that from fluctuating too much, right? One of the things you will commonly see right now, in fact, I was just scrolling TikTok a little bit ago and I saw it. Somebody was taking the pH of water and talking about how acidic it was or how basic it was. The problem with that is the water's not buffered, and as soon as you add a little acid to it, then the pH just drops super low. Buffers prevent that violent swing in pH. Your body is heavily buffered. Your blood is heavily buffered because you don't want your blood to change. Your blood pH 7.35 to 7.45. That's a narrow range. You don't want that to change very much. And the way your body maintains that is through your respiratory system and through your kidneys. Drink all the alkaline water you want. Drink all of the, people will tell you that alkaline water is somehow better for you because it helps keep your body from being acidic. Again, your body's going to say 7.35 to 7.45 unless there's something drastically wrong. In fact, if your body starts to if your pH starts to drop to this 7.35 and maybe slightly lower, one of the things that'll happen is your respiration rate will just increase a little bit. Right? You'll drive off some CO2 and that'll bring your pH back up. If the pH gets a little too high, so a little close to 7.45, you can slow you won't, not consciously, but you might slow your breathing rate down a little bit, and that'll help maintain. The other thing that can happen is with your kidneys. So if the pH starts to get a little too low, well, you'll just excrete excess hydrogen ions, and that'll help you maintain. So the idea of drinking acidic things or basic things to help regulate your body's pH, there's not much legitimate science to that, and usually they're trying to sell you something when they're talking about those things. Actually, the idea of that of acidic things being bad for you came from cancers. So what people found out, and this is typically of a lot of myths, the way they happen is they'll take a little bit of science and then it gets distorted. So what we have found is that cancers, around cancerous tissue, it tends to be somewhat acidic or more acidic than you would expect in normal tissues. But the reason that is because cancer cells tend to go through glycolysis much more quickly. And we can talk about the way they go through metabolism and things like that, but that causes those environments to be a little bit more acidic. It's not the acid that causes the cancer. It's the cancer that causes the acidic nature of those tissues. And so, again, one of the problems here is it creates unhealthy relationships with food, and that people aren't eating things or are eating things based on some faulty knowledge of pH, right? And that kind of gets some highlights, although I've been going at it now for 33 minutes, right? I love this stuff, so I can talk about it forever. But just wanted to give you some things to kind of think about there. Obviously, you don't have to watch this video if you've made it this far. You have watched it all. Don't necessarily watch these videos all at one sitting, kind of break them up into parts. And maybe as we go through, I can do a little better job and maybe make individual videos on individual sections. But anyway, I hope this helps a little bit. If you have any questions, please let me know.